Okay, people, let's get started. Please turn on your video if you're comfortable with this. Otherwise, get ready with the icons. So, today we're going to talk about Taylor and Maclaurin series. So, this is about the possibility of representing functions as power series. So, and there's a massive advantage for being able to do this. So as we've learned previously, once we have a power series, then in its interval of convergence, every possible good thing we want to happen actually does happen. We can differentiate this term by term, just like a polynomial. We can integrate this term by term, just like a polynomial. It is, for all practical purposes, just as nice as a polynomial. And a polynomial is one of the nicest functions you can have, right? So if you can actually represent a function like this, then all the difficult things we've been doing, such as finding antiderivatives, explicitly calculating integrals, becomes very, very straightforward once we have such a representation. Okay? But it doesn't come for free. So not all functions have representation. A very large class of them do. Most of the functions we actually deal with will have. And secondly, the representation isn't necessarily going to hold everywhere. So the function can be defined everywhere or in some large set. The representation might only hold within some part of that domain. And these are things we have to pay attention to. But first of all, let's see what possible representation we can have. In other words, suppose we do have representation, let's find out what these CK are. Okay. So let's call this star. So if star holds for some radius of convergence, so this series is centered around the number a. So for all x minus a less than r, and we're going to assume that r is actually positive, so there's a non-trivial interval where this is actually true. Then what's the first thing we can read off about this? Well, if we simply stick in x is equal to a into this expression, well, what do we see? So let me first expand it so it's clearer for you. So when k equals 0, we just have c0 because x minus a to the 0 is just 1. And the next time is c1, x minus a. Next time is c2, x minus a squared, and so on like this. So if we simply stick in x is equal to a, we find that c0 is equal to f of a. Yeah? Because every other term just vanishes. So we know the first coefficient c0. Yeah? But if we have this expression like this, as we've learned, we can just differentiate this and we have another power series. The power series now represents the derivative. Yeah? So, and we know that f prime of x is what happens when we differentiate this thing. The constant term just vanishes. So we have k equals 1 to infinity, and then we're going to have ck x minus a to the k minus 1, and then the first term is just going to be c1, and the next term is 2c2 x minus a, and the next term is 3c3 x minus a squared, and so on. Yeah? Give me a thumbs up if you're with me here. So we have a lot of content to cover, and this is one of the more subtle things we're going to talk about. Okay, cool. So, sticking in x is equal to a into this, again, we'll learn something. We'll learn that c1 is equal to f prime of a. Yeah? Cool. And then we do this again. And differentiate again. So now, the k equals 1 term, which is a constant, drops. So we start with k equals 2. And what happens? We're going to have k times k minus 1, ck x minus a to the k minus 2. And then the first term is 2 times c2. And then we're going to have 3 times 2 times c3 x minus a. And then we have 4 times 3 x minus a squared. And then so on, right? And the same procedure. Stick in x equals a, and we learn this thing. C2 is equal to 2 f double prime. Do this properly. So f double prime of a is equal to 2 c2. So let us divide by 2, and we have that c2 is equal to f double prime of a over 2. Okay, let's do it again. Third derivative. K equals 3 this time to infinity. K minus 1. K minus 2. X minus a to the k minus 3. The first term is now 3 times 2, c3. And the next term is 4 times 3 times 2, x minus a. And the next term is 5 times 4 times 3, x minus a squared, and so on. Stick in x equals a, and we have that c3 is equal to the third derivative at a times 3 times 2, which is the same as 3 factorial. Yeah? And we'll just keep going. And every time we do this, we're going to find out another coefficient, right? And the general formula, as you can sort of see, is going to fall out from this pattern, is that the kth is going to be the kth derivative over k factorial. Yeah. So if there exists a... All right, thank you. Cool. So this is our general expression. Yeah. So if this thing holds, so if star holds, then we do indeed have that. It has to be represented like this. Yeah. And this thing is called the Taylor series. So Taylor series from now on will be T series. And if A is equal to 0, it's called Mclaren series, which I'm going to call the Mac series. Okay, let's write out the first few terms. So fx is equal to f of a plus f prime x minus a plus f double prime of a over 2 x minus a squared, and so on. And on like this. Yeah? Cool. All right. So look at this expression carefully and then think about where you've seen things like this before, what this can mean. I'm going to raise the board. I'm going to ask you to explain what this stuff is. What this stuff is after we erase the board. Let's look at what we established. So if f has a power series, in the interval a minus r, a plus r, then we have that, put it over here, f of x is equal to the sum from k is equal to 0 to infinity of f to the k at a over k factorial x minus a to the k, and the first terms are f of a plus f prime of a x minus a plus f double prime of a x minus a squared over 2 plus the third derivative at a over 3 factorial x minus a to the 3 and so on. Okay, so let's draw a picture. We have a is right here. We have some function, yeah, like this. We have some interval. The interval could be the entire real numbers, or it could be 0 to 1, or whatever, or a to a plus 1, a to a minus 1. Yeah, it could be not that small, but it might be small, who knows. Yeah, and what that says is that on this interval, this function is represented by this thing right here. Now, suppose we looked very close to a. If we look very close to a, which are the important terms of this series? Which are the important terms? Well, the last one there isn't because it's infinite, right? So this goes off to infinity. So the first one and the second one, yeah? And the third one if you want. So if you let x get very close to a right here, yeah, then this guy is the constant. There's this term, and all of these guys are smaller the further right we go, right? The further right we go, yeah? And this thing, if we don't have the entire series, if we just cut it off somewhere, then it's not going to be the actual function, it'll be an approximation to the function, yeah? Yeah? So let's see what happens if we just cut off every term except the first term. Yeah, let's see what happens. Well, then we just have the function, the constant function, f is equal to a, like this, right? And that is some kind of an approximation to our function, right? When x is close to a, then f of x is close to f of a. That's true. That's continuity, yeah? It's not a very good approximation, but it's some kind of approximation, yeah? What happens if we take the first two terms? Tell me where you've seen this expression before. Yeah, this is just the tangent line, right? This is just the tangent line. So recall the t-line to f at a is just given by this. Is equal to f prime of a x minus a plus f of a, right? Because this thing has the slope of the function at a, right? It's a linear function, and when we stick in x equals a, we get the function itself. So it's going through the point a, f of a, and it has the same slope as the function at that point. This is the tangent line, right? Yeah? So if we did a slightly less crude approximation, and we took just the first two terms, we have exactly the tangent line, which is an object we know very well, right? So we've talked about tangent line a whole bunch, right, during last semester and also this semester. So this is the tangent line, T1. Let's call it T1. And let's call this thing, where we just take the zeroth term, the constant term, let's call that T0. Yeah? So the tangent line does a better approximation than the constant function by quite a bit, right? If we have the right to slant something in the direction of the slope of the function, then that is locally a much better approximation than just the constant function. Yeah? Yeah? See what I mean? Yeah? Cool. But if we want to get even more fancy, we can take the first three terms. So we have the right to put something that bends like a quadratic in the mix. Yeah? And if we do that, we can do yet still better. We can do something that will fit even closer to our function around a itself. Let's call that t2. Yeah? So as we have more and more of these terms, we are doing a better and better job of fitting the graph, right? Doing a better and better job of fitting the graph. Yeah? And the essence of this is that when we do have the existence of a Taylor expansion, a Taylor series, we can actually keep doing this, adding term after term after term, and completely fit the function. We can completely fit it. Yeah? That's what's actually happening here. Yeah? And once we've done that, once we have this possibility to keep adding all these terms and have something that fits the function and is a power series that converges, then, as I said, all the good stuff follows. We have something which is just as good as a polynomial for all the calculations we want to do. Well, not quite just as good, but almost as good. Almost as good as a polynomial. Yeah? Something that's very much like a polynomial, and anything where it differs from a polynomial, that error is calculatable, as we'll see later. Cool. All right, so that's the point of this. That's what we're doing. That's the essence of this. Let's do an example. Example 1. Assuming the max series of e to the x exists, because I haven't told you anything about when it exists yet, I'm just assuming it does. Calculate the series and its radius of convergence. Okay, so solution. Let's write f of x is equal to e to the x. So differentiation is trivial because it's always the same function. So the kth derivative of our function is just e to the x. Yeah? So the formula for the coefficients of the power series, since we're doing this, it's a max series, we're doing this around 0, right? It's just e to the 0, which is equal to 1 for every single k, right? So the series is really easy to write down. So e to the x is therefore the sum from, I'll write it out, the actual expression for the general expression for the max series. So it's this, right? This is what we've learned, just sticking a is equal to 0. It's a max series, it's around 0. Yeah? We know this is always equal to 1, so it's just this. Yeah? Very straightforward, right? So that was the first term. The first term is when x equals 0, we have 1. The next term, when x equals 1, we have x. The next term, when x equals 2, we have x squared over 2. And so on like this. Yeah? Next term, x to the 3 over 3 factorial, and so on. Cool. Let's see if we believe this. Let's see if we think that this does a good job of approximating our function. What does e to the x look like? It goes like this, and then it blows up very, very fast like this. Yeah? So, the zeroth order approximation, when we just take the first term, we just have the constant 1 like this. Yeah? When we take the first two terms, this is indeed the tangent line, right? And that indeed fits the graph kind of well, so long as we're close enough to 0. Yeah? But this guy, we're allowed to add a quadratic, allows us to bend this thing more like the way the graph is actually bending. So say it's looking something like this. Yeah? So this is T3. So this is T2, this guy's T1. So these coefficients are convincing to us, right? Because we can calculate the tangent line, the derivative of the function at 0 is just 1. When we put in 0, the function is equal to 1. So this is indeed the tangent line, right? Yeah. So this is looking like it's giving a meaningful, correct answer for what a power series should actually be. Yeah. And we're assuming that the power series actually exists. All right. So this is our power series. Let's find its radius of convergence. So we know how to do this. We practice this for a bit. So to find its R of C, let A n be, let's do a k be x to the k over k factorial, then absolute value of ak plus 1 over ak is just going to be absolute value of x over k plus 1, and that tends to 0 no matter what choice of x we have. Yeah? Which means that this thing will converge as a series no matter what choice of x we have, right? The radius of convergence is infinity. Yeah? So series always converges. And if you're, as you've done a number of exercises like this, you're kind of familiar with things like this, where a power divided by a factorial is always going to converge everywhere. So series converges. So that's cool. So we have a nice, neat, simple-looking series. And we have that it actually converges everywhere. So if we knew that the series was actually equal to the function, then that would be great, right? That would be great. Then we could, instead of dealing with this guy, we can deal with this power series, and a lot of things become easier. Yeah? Everybody happy? Everybody with me? Okay, so I've got a lot of ground to cover, but it's no point unless you're all with me. So do speak up if anything's unclear. Speak up if anything's unclear. Okay. Looks like we're all good. All right. Okay, so we define the nth degree Taylor polynomial as follows. So Tn x is the sum from k is equal to 0. Write that better. Up to n of this general expression. So f k a over k factorial x minus a to the power k. So first term, as always, is f to the a. Next term is f prime a x minus a. Next term, prime prime 2 squared dot 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 until the last term is the nth degree term. So it's a polynomial of degree n. We take it up to n, and then we stop. So T0 is just a constant function. T1 is the tangent line. Right? And we define Rn of x to be the difference between the function and the nth degree Taylor polynomial. Yeah? So let's draw the picture again. So we have a like this. We have some function. And suppose we have some interval we're interested in like this. Okay. Then as we put more and more terms in, as we've seen, the Taylor polynomial fits onto this graph better and better and better. right? That's the point of what we're doing. And Rn says how far the nth degree polynomial is actually away from the function. Okay, so Rn of x depends on what x we are at. So suppose we have this guy is our x, then the gap here between the function and the nth degree Taylor polynomial is our Rn, our remainder, our error. Okay. So to say that we have a power series expansion is the same as saying that as we let n go to infinity over some interval, this Rn is going to go down to 0, right? Because Rn is how far the nth degree Taylor polynomial is from the function. And if we know it goes down to 0 over every x in some interval, then that says that as we take the limit of the partial sums, we have the actual series, that series will exactly match our function. Do you see what I mean? Yeah? Thumbs up if you're with me. Okay, cool. So what we need to do is to guarantee that there exists some interval where this guy actually goes down to 0, right? And that comes down to the following theorem, which seems a bit technical, so I'll write it down and then I'll explain it, and hopefully it'll seem less technical after I explain it. And as always, this theorem has a nice picture, but in this case, it's more than one picture, and I can't explain it in pictures in this course. So you're going to have to just trust me on this, but I will motivate why this is a natural thing by analogy rather than by pictures. Analogy to other things we studied. So Taylor's inequality. So this is Taylor's inequality, that we have that n of x is less than or equal to m over n plus 1 factorial absolute value x minus a to the n plus 1, where m is equal to the supremum of the absolute value of the nth plus 1 derivative over the derivative, over the interval we're interested in. This. So, what does that mean? So that we have some interval like this, okay? And we take this nth plus 1 derivative, it's some function, and we're going to take its supremum, its maximum value. You don't want to put maximum because you're more familiar with that word. We take its maximum over this closed interval. It'll be a continuous function. It will have a maximum. We studied this stuff a lot, right? So whatever that maximum value is, then this expression here is bounded by that maximum over the interval times this expression. Okay, looks technical, but let me explain it. So remember when we talked about alternating series, right? We went backwards, went forwards, and we went backwards, and went forwards, went backwards, right? And we stopped here after doing n steps, yeah? And then all the other steps we took, right? So forwards, backwards, right? They were trapped here, somewhere here, where this distance here is the bn plus 1 step, right? This is bn plus 1. Yeah? So whatever the actual answer to the series was, it's somewhere which is trapped with distance maximum bn plus 1 away from the Sn step. So we know that the actual sum, Sn, which was the sum from k equals 0, infinity, minus 1, k minus 1, bk, is such that Sn minus the nth step is less than the bn plus 1 step size, right? This is what we learned, or less than or equal to, yeah? Yeah? Give me a thumbs up if you remember this. Cool. Now, what I'm hoping to convince you or sell you on is that this is morally the same kind of thing. This is like the nth plus 1 step inside our Taylor expansion, right? Because what is the nth plus 1 step? So let's change color. So like the bn plus 1 term in an alternating series, because of what? What is the bn plus 1 term? The bn plus 1 term in Taylor series, can't spell series, is n plus 1 of a x minus a to the n plus 1 over n plus 1 factorial, yeah? So it's like the bn plus 1 term, but it isn't actually the bn plus 1 term because we can't just put in the nth plus 1 derivative acting on a. We need something a bit stronger. We need to take the nth plus 1 derivative where it's allowed to move over the interval and take the maximum of that. So it's like the bn plus 1 term, but a bit stronger. We need something a bit stronger. Okay? And why should you think of this as being reasonable? Well, this is why. If you have this general expansion, Taylor's inequality, if this general expansion, Taylor's theorem, right? This holds true for all x, right? Within whatever interval. So this is Taylor's expansion, right? So we have f of x is equal to the sum from k equals 0 to infinity of k derivative at a, k factorial, x minus a to the k. And as x moves around, these guys here will change sign, right? These guys here will change sign. Yeah? So when k is even, no, it won't notice. When k is odd, it will notice. If x is bigger than a, it'll be positive. If x is less than a, it'll be negative. Yeah? Yeah. So in some sense, this guy, the Taylor expansion, the Taylor series, is a bit like an alternating series, but it's an alternating series where we have the right to shift the x around. Yeah? But the nature of it is that these terms will flip signs in many cases. Right? Yeah? And it's a little bit subtle because it doesn't always do this. If these coefficients also flip signs, then that sign flipping property will change. But in the simplest case, when this is just remains the same sign, either positive or negative for all k. So if this thing remains either positive or negative for all k, then this thing will be an alternating series. Yeah, this thing will be an alternating series. Yeah, and then this Taylor's inequality follows from the fact that we have the alternating series error estimation. Yeah? Because this expression here is bigger than the bnth plus 1 term. Yeah? So in a special case, we can sort of see that this isn't that surprising. It's kind of similar to what we've seen before. In the general case, there are reasons very much like this why this is true all the time. And I can't explain it in this course. Hopefully we'll study maths at a higher level and you'll see an explanation. But what I want to do just today is just for you not to be scared of this expression. Not to think that this is some kind of weird, complicated, difficult thing that you'll never understand. I guarantee you if I had half an hour, I could convince you of this in pictures and you wouldn't think it was strange at all. But I don't have half an hour on this. So all I can do is say, metaphorically, this is a lot like the bnth plus 1 term, and therefore it's not such a surprise we see such an expression. Yeah? So don't be scared of this inequality. This is not so weird. This is nothing particularly complicated. It is a lot like this. Okay, cool. So with this thing, we can actually tell whether or not we have the possibility to expand in a Taylor series, which we haven't done so far. So far, we just assumed we have one, and just example 2, prove that EX is equal to its power series. Well, solution. We know that Rn of x, which is equal to just our function e to the x minus the nth Taylor polynomial, has this nice convenient inequality. And we're doing this around 0, so this is x to the n plus 1 over n plus 1 factorial, where n is equal to the max of the nth derivative of this guy, also n plus 1th derivative, but the nth plus 1th derivative is just e to the x as well, so the max of e to the x over the interval, let's take some interval minus r to r, okay? So we'll start by picking some number r, so let r be bigger than 0. And let's try and show that this thing is equal to its power series expansion over this radius of r from minus r to r, okay? So we have that this is true, right? And this thing, its maximum value is when x is actually equal to r, so this is just equal to e to the r. Okay? So n of x is less than e to the r x to the n plus 1 over n plus 1 factorial for all mod x less than r. That's just what Taylor's inequality tells us, right? Then, what happens to this expression as we let n goes to infinity? Well, if you look at this, r is e to the r is just some fixed number. Maybe it's very big, we don't care, but it's just fixed because we're letting n go to infinity. And then this is a fight between x to the n plus 1, which should be absolute value, and n plus 1 factorial. And we know which is going to be the winner of this thing, right? So this is just x, absolute value multiplied by itself, n plus 1, and on the bottom we have n plus 1 factorial, which is blowing up a lot faster, right? We've seen this kind of thing before, right? So this is equal to e to the r, x times x times x lots of times, right? Over n plus 1, n all the way down to 1, right? And as n gets bigger, then these terms are mostly bigger than the x's, and this thing goes to 0, right? Yeah. So that says that for fixed we have that n of x goes to 0 as n goes to infinity, no matter what x we have, right? So for any x whose absolute value is less than r, right? So let's draw the picture. We have, it's not a very straight horizontal graph. we have our exponential function like this. We've taken some r. So this is r to r. And we know that no matter what x we have inside this interval, take any x you like, then as we let the n go up to infinity, we have more and more terms in the Taylor polynomial. Then the gap between the nth term Taylor polynomial, Tn, and the actual function, e to the x, is going down to 0. So this thing is n to the x, and we know it's going down to 0 as n goes to infinity, which exactly says that if we take the actual limit as n goes to infinity, which is the definition of the Taylor expansion, right? So the sum from k is equal to 0 to infinity. Actually, let's put in directly what the expression is of x to the k over k factorial. This is the limit. That's what an infinite series is. That's the whole point of all the stuff we've been learning. This is the limit of this thing. In other words, it's the limit of the nth degree Taylor polynomial. Oops. Okay. And that thing is looking more and more like our actual function, right? E to the x minus Tn of x, absolute value, is equal to Rn of x, which is going down to 0. So e to the x is actually equal to the limit as n goes to infinity of Tn of x, which is, by definition, the full series. For all x in this interval like this. Yeah? So all I've done here is write in the language of maths what I see here in this picture. That's all I've done. Yeah? So cool. That means we actually do have this as a true thing. And notice that I picked r to be any number. So it could have been 10, could have been 1,000, could have been 10, 100 trillion zillion to the power 99, whatever. Doesn't care, doesn't matter. As n goes to infinity, no matter how big an r we take, this becomes bigger, but we don't care because this entire thing is going down to 0 as n goes to infinity. So this actually holds true for every single r, which means it holds true for all x. Right? So whatever x you're interested in, for sure it's inside some interval from minus r to r for some big R. And that is actually true. This expansion is true inside that interval. So it's actually true for every single x. Yeah? Cool. So e to the x is the very nice situation of having a Taylor, this is actually Mclaren because it's centered on 0, a Mclaren series that holds true, that represents it for every single x. Yeah? And the Mclaren series itself has a radius of convergence, which is infinite, right? So we can stop worrying about e to the x as a function now, and we can now think about it as a power series, and we never lose anything because it's completely equal to a power series. It's equal to a power series everywhere. Yeah? Everybody with me? And a neat thing you can just observe here, I mean, the point of e to the x is if you differentiate it, you get it back again. If you differentiate this expression, you'll see that you get back exactly the same thing. Just differentiate it term by term. Yeah? So, part A. Express the integral of e to the minus x squared dx as a series. And part B, calculate or approximate this thing, so the same function, let me write it better, to within 0.01. 0.001. Okay. Why is this cool? This is cool because this is something we can't do with many calculus methods, right? Try all the different things you've learned: substitution, trig substitution, integration by parts, U substitution. On this guy, you won't get anywhere, right? This guy, it's very simple looking expression, but all of our tools just collapse. Yeah, they just bounce off this guy and you can't do anything. Yeah. So let me write it down, it's so important. So our tools so far do not help. With finding this thing. Give it a shot if you want, but we can't do this guy. Well, can't do this guy. But we do know that e to the x has got a power series expansion that converges everywhere. All right? So we know that e to the x is equal to the sum from k equals 0 to infinity. Actually, let me call it e to the y, because x is already there. So let's call it e to the y. It's equal to y to the k over k factorial. And this works for every single y on the real line. This is true. This is what we've just shown. Yeah? So we could just let y be minus x squared. Yeah, because minus x squared is just a number. We can just put it into this expression, because this expression is always true. So e to the minus x squared is equal to the sum from k equals 0 to infinity of minus x squared to the k over k factorial. And then this is the sum from k equals 0 to infinity of minus 1 to the k x to the 2k over k factorial. Cool. So what we've just written down is a Mclaren series for our function e to the minus x squared. And now we're super happy. We're jumping up and down happy because we know that when we have power series that converges everywhere, which this thing does, we can do all the stuff we want to do as if it was a polynomial, right? And if this is a polynomial and we're integrating it, then it's very easy. We integrate it term by term, which we know is true also for a power series. So the first part now becomes easy. So integral e to the minus x squared dx is the integral of this thing yeah, and just like as if it was a polynomial, we can just integrate this term by term, right? So then that's the same as the sum k equals 0 to infinity minus 1 to the k over k factorial of the integral of x to the 2k right? And then what's this? This is the sum from k equals 0 to infinity minus 1 to the k over k factorial. We can certainly integrate x to the 2k. It's x to the 2k plus 1 over 2k. And we have some constant c that comes in. But a constant is just a constant, and we add constants, it's still a constant. So we'll put the constant on the outside, so plus constant c like this. Yeah? Cool. Everybody happy? Yeah? And then this is the answer. This is another series that that converges. Right? This, you can check this easily. With this k factorial on the bottom here, kills everything. So this guy will definitely converge. So we have exactly what the antiderivative of this function is. It is given to us here as a power series. And maybe you feel this is less satisfactory because you're used to finding antiderivatives of some explicit function. Yeah? But what you have to get into the mindset of is that when we have a power series that converges, that's just as good as an explicit function. In fact, it's better. Yeah? So we have an explicit answer. Yeah? And to prove you that it's actually just as good, or even better, we're going to do this explicit thing of finding this definite integral, right? I'm going to find this definite integral. So part B. So to find this guy, which, pre-computer days, this could well be something you need to do to build your steam engine, to build your aircraft, whatever. You easily come up with functions to describe things you want to calculate in order to build what you want, and you want to find their integral, and this is how this was done pre-computer days. In fact, it's how it's done now, except it's just a computer does the calculation for you. Yeah? So what we do, we have this thing right here. We have the antiderivative, right? Antiderivative is this power series. Right? And then we just do what we know how to do. We're going to stick in x equals 1 into this expression, and we're going to stick in x equals 0 into this expression. And when we stick in x equals 0 into this expression, the only thing that survives is this constant c. Right? So the constant will vanish, as we're used to happening when we evaluate definite integrals. So sticking in x is equal to 1, what we'll have is the sum from k equals 0 to infinity, minus 1 to the k, over k factorial. And then just x equals 1, this will just be 1 over 2k plus 1. And that's it. And then this is an explicit series, right? This is an explicit series. So this thing is the answer to this definite integral. Yeah? What kind of series is this? It's alternating. So why are we happy with alternating series? Why do we like them? And does this converge? Yeah, very much converges. In fact, it converges absolutely. It's going to 0 pretty fast. Very fast. Yeah, extremely fast. Okay, and what's another good thing we like about alternating series? Right. We can approximate the answer very easily with this alternating series error estimation test, right? Yeah. So our task was to find this to within 0.001, right? So we need to find the bn plus 1 term, which is underneath, which is smaller than 0.001. And the first one we do, we stop just before that, right? That's the alternating series error estimation test. So if we just write out these terms here, so when k is equal to 0, we have 1 to the 0, 0 factorial is just equal to 1. So the first term is just 1, right? So then we have 1. When we put in k equals 1, we have minus 1 over 1 over 3. So we have minus a third. When we put k is equal to 2, we're going to have 2 factorial, which is 2, and then this will be 4, this will be 5, so it'll be like 1 over 10, right? So we're going to keep doing this until we find the guy which is less than this thing. So what is this thing? 0.001. Let's build it up. So 0.1 is 1 over 10. 0.01 is 1 over 100. So this thing is 1 over 1,000. Right? So we're going to keep doing this until we find the term which is less than 1 over 1,000, then we stop just before it. So the next term, I've got this prearranged, but if you stick in k is equal to 3, this then turns out to be minus 1 over 42. The next term, it is 1 over 216. The next term is minus 1 over 132. So this guy is less than 1 over 1,000. So that's the bn plus 1 step. That's the guy that we've been looking for. This is the bn plus 1, right? So if we stop after these terms, we have our answer to within 1 over 1,000. Yeah? So by alt series error estimation, the answer is this thing, 1 minus 1 over 3 plus 1 over 10 minus 1 over 42 plus 1 over 216 approximates our integral to within 1 over 1000. Yes. From 0 to 1, e to the minus x squared dx to within 0.001, right? And this is a real practical world-building consequence. We could not do this without this method. We couldn't answer the question of what this is without this method, right? It's just out of range. So if you are stuck on your physics, engineering, chemistry problem, and the answer does depend on something like this, if you didn't have a Taylor series, then society, technology wouldn't have progressed because you just wouldn't know how to do this. You would have no clue, right? So this is why we spend so much time teaching you about series, getting you comfortable with series so that we have this power to expand functions as a Taylor series and do explicit calculations that are out of range otherwise. Yeah? And when you are applying software, the reason it works is because it's doing exactly this kind of stuff, right? And the limitations of what it will do is because it's doing this kind of stuff. So that's really why you as engineers are here. So you understand what is actually happening when your software is calculating your answer and when it's actually going to give you something reasonable and when it works. So if you're calculating like this, the software will give you something reasonable, but in the future, there'll be other reasonable looking problems where your software will give you complete nonsense. All right. So that's the main payoff I wanted to tell you. Okay, so we can calculate the Mclaren series of other functions. So this is another example. Find the Mac series of sine of x. All right, so since we know what the general formula is, so let's f of x be sine of x, right? So we know that the general formula will be this. So it's a Mac series, so we're doing this around 0, and then x to the k. We just have to calculate these coefficients, right? So let's just write them out here. So f of x, let's take the first derivative, it is going to be cosine of x, right? Let's take the second derivative, it is minus sine of x. Let's take the third derivative, it is minus cosine of x. And let's take the fourth derivative. It is now sine of x again. And then it's going to repeat, right? Because we are back at the zeroth derivative when we have sine of x, right? Cool. So we need to stick in the values when x equals 0 to read off what this thing is. So when x equals 0, so f of 0 is 0 here. F prime of 0 is 1 here. F double prime of 0 is 0. The third derivative of 0 is minus 1. And the fourth derivative at 0 is 0. Yeah? So we go 0, 1, 0, minus 1, 0. Yeah? And then we repeat. Yeah? So let's work out what we've learned. So we've learned that whenever we have an even number of derivatives, where 0 is even, right? Then there's nothing there. So the only things that come out from this expression are the odd powers. So let's do this. Equals 0 to infinity, f to the 2k plus 1, the 0 over x to the 2k plus 1. over 2k plus 1 factorial, like this. Yeah? That's the way it's got to work. Yeah? Cool. And then if we look at the structure of the odd ones, so when we are at 1, we are positive 1, and when we're at 3, we are minus 1, right? Yeah? And then it'll repeat. So these numbers will either be 1 or minus 1. And let's see what they are. So when k is equal to 0, we have the first derivative, which just gives us 1. And when k is equal to 1, we have 2 plus 1, which is 3, which is minus 1. Right? So, and then it repeats. So we get that this thing will be minus 1 to the k, x to the 2k plus 1 over 2k plus 1 factorial. Yeah? And that's it. And for very similar reasons as to why the Taylor expansion b to the x exists, this thing also exists. This thing actually does represent this function. And it's not hard to check that this holds true. The power series expansion, firstly, this thing converges for every single x. This 2k plus 1 factorial forces it to go to 0 fast enough that this thing is always going to converge for every single x. And the same estimate we used using Taylor's inequality shows that this thing actually does represent this thing. Yeah? So this holds true for all x. So we no longer have to worry about our sine function as a function. We now have it as a power series, and all the good stuff follows. So the good stuff that I did in the last example, being able to explicitly calculate the integral of e to the minus x squared. We could do this with sine of minus e to the x squared, or whatever, something in sine, some power inside sine, we can still explicitly calculate because we have this power series. So it's very useful to have power series expansions, and there are a bunch of power series that you need to know. And the best way to know them is to work them out and not attempt to memorize them. You have to choose your own method. It's not particularly hard to work out these things. So you can work out the power series of cosine, work out the power series of a whole bunch of things. And I'm just going to list a few examples. So, examples. So our first guy is this guy. This is the first guy we learned. This is a power series expansion, and this is the Mclaren series expansion with this function around 0. Yeah? And if we learned this thing only holds true for mod x less than 1. Even though this function is defined for every x not equal to 1, right? This thing is only holding true here in this range. But for calculations in this range, this is very useful. So e to the x we've just learned. Sine we just learned. Let's write it again. Cosine is like this. And work out in exactly the same way. Notice that this is an even function. As we let x be either minus x or x, it doesn't notice it because of the even powers. It's an even function, which is what you'd expect. Tan to the minus 1 is this thing. And log of 1 plus x. So for reasons having a neat expression, we write log of 1 plus x instead of log of x. And it turns out to be this thing. Again, all these things you can easily calculate and verify for yourself. Okay, so And not all of these guys have a radius of convergence that converges everywhere. So, example, this guy tan to the minus 1. I'm not going to try and calculate its radius of convergence, but I think it's going to be between minus 1 and 1. This guy will converge everywhere. This guy will converge everywhere. This guy also, I think, between minus 1 and 1. All right, so what's good about this? Well, you might remember that I told you that whenever we are asked the question explicitly calculate a series, then it's either going to be a geometric series or it's going to be a telescoping series, because that's the only methods we have, right? Those are the only methods we have. And I added a caveat, until we learn future stuff. And the future stuff is this stuff, Because once we have these power series expansions, then we can explicitly find out some series by knowing these expansions. So here's an example. Example 10. Find the sum of this thing. 1 over 1 times 2 minus 1 over 2 times 2 squared plus 1 over 3 times 2 to the 3 minus 1 over 4 times 2 to the 4, yeah? And so on, plus. So the hint is it says find the sum of, so there must be a way to actually explicitly find what this is. And it's not either a power series or a telescoping series. So what it will be what happens when you stick in some explicit value into one of these known Taylor series, right? And if we look at this list, so all of these are powers in X, right? So looking at this thing, the natural conjecture for the power of X is X equals a half. So we guess X is equal to a half, because then we have a half squared, a half to the 3, a half to the 4, a power, right? Power is expansion, yeah? So if X is a half, then what coefficients will be such that it goes 1 minus a half plus a third minus a 4? And we look down this list, and this guy is our guy, because if we write out the first terms of this, then when n equals equal to, should it be n equals 0? I think not, n equals 1. If we look at this list, just 1, because minus 1 to the 0 is just 1. So then we just have X. And then when we let X equals 2, we're going to have minus 1. And then we're going to have X squared over 2. And then X is equal to 3, we're going to have plus, and we're going to have X to the 3 over 3. And then you see what's happening, right? X to the 4 over 4, right? Which is a lot like what's happening here, because if we let X be 1 over 2, then we have first coefficient is a half, first coefficient is 1, next one's minus a half, then plus a third, then minus a quarter, which is exactly what we see here, right? So we guess equals half, then sticking in into this guy here, let's call this guy star, we have that log of 1 plus a half, which is log of 3 over 2, is exactly this series. Call this thing star star. So we have explicitly what this thing sums to, and it sums to this particular expression here. All right, so this kind of question is a way to test your knowledge of Taylor series, or Mclaren series of standard functions. It is useful to know these basic expansions, and this question tests your knowledge of those. So you will see homework questions like this, where you're asked to explicitly find some sum, and if it's in this section, then it means that you will get explicitly what this is by putting in for some value of X into one of these Mclaren series, and then you'll see exactly this thing. So it's not a particularly difficult question, but you have to extract out what is the X, what is the thing being taken to some power, right? And then the other stuff will just be the coefficients. So then you just read off what the coefficients are to pick out the right series. Cool. All right. So that's finally it. That's enough for you to do the homework to be able to answer these questions. Is everybody good? Those of you who are still here, do you have any questions before I say goodbye? No? Everybody's good? All right. So have a good day, and I will see you all next week. Bye-bye.